Morning, guys. Today I'm going to go over some of the notes on the charge section, so we don't have to do that in class. Some of you have already gotten through this slide, but it's okay. I'll go through it quickly. All right, so in order to understand how these things are interacting, we need to know what makes up an atom. An atom has two main parts. It has a nucleus and then everything else around it. In the nucleus, we have the neutrons and the protons, which gives us almost all of our mass, the protons being positive, the neutrons being negative. And then existing somewhere outside of them is the electrons, and that makes up 99.99% of the atom. So mostly atoms are in extra space. And you guys saw this when in chemistry they talked about Rutherford's experiment, where he shot the alpha particles through the gold foil that he had really thin, and most of them made it through without being affected at all. The important thing to note is that a proton has the same amount of charge as an electron, so that is going to be our elementary charge, our quantized amount of charge. The protons and neutrons have almost exactly the same mass. Electrons have a negative charge, and they do have a mass, but protons and neutrons are about 1,800 times as massive, so we really don't take into account what the mass is of an electron. Most things that you deal with have the same amount of electrons and protons, and so they're neutral, and so we don't have a net charge on anything. You can put a net charge on from one thing onto the other by doing work on the object with friction, and you'll have a transfer. So in our picture here, we see that the pieces of paper are now being attracted to this ruler because this ruler has an excess amount of charge. When they made up what these things were, they made the value for what a coulomb was very large. And so it turns out that 1 coulomb of charge is going to be a super large amount of electrons. So 6.25 times 10 to the 18th electrons. That's a lot of electrons. This is named after Charles de Coulomb, who is going to be the person who is going to have the equation of how charge attracts other charge, named after him. It turns out that if you have the same charges, they're going to repel, and unlike charges attract. The only way to know if two objects are charged is if they repel, because we've seen that uncharged objects will attract a charged object. So we just need to remember that opposites attract, like the classic Paula Abdul song from the 80s. So here's an example. We have positive and negative. What charge is called positive and what charge is called negative was an explanation by Franklin. So if I have two negative charged rulers, they're going to repel each other. If I have two positive charged glass rods, they're going to repel each other. And if I have a negative charged ruler and a positive charged glass rod, they're going to attract. But a neutral glass rod and a negative charged ruler would also attract, and so would a neutral ruler and a positive charged glass rod. Some objects are overall neutral, but they polarize on their own. Water's one of these. So the molecule itself has a negative side and a positive side, but overall it's neutral. So we looked a lot in those demonstrations about conductors and insulators. A conductor is going to be something that lets charge flow freely. An insulator, the charge is going to have a tough time moving about. It's not to say that it can't move, and we saw this in the demonstrations as well. So a good example of this would be Deborah. the charge does flow through her hair and get far out, but it takes a huge amount of potential to get this to happen. Conductors are typically metals. Insulators are pretty much everything else. So if I have one object that has a net charge and one object that's neutral, if I touch them together with the conductor, the charge is going to spread out as far apart as it can. If I touch it together with an insulator, nothing's going to happen. So the insulator is not going to allow the charge to easily flow through this. And this has to do with how the atoms themselves are made up. So typically metals have a lot of loose electrons that they're already readily sharing with the atoms next to each other. And so if you provide a path, it's easy for them to move. So good conductors are going to have loose electrons. I mentioned this and we saw it a little bit. Most things are neutral. You can make them behave like they have a net charge by bringing something charged close to it. We saw this with the virtual balloon, but this has the same amount of positives as negatives. If I bring the negative close to it, we'll have negatives that will migrate away from this negative because they don't want to be close to it, leaving a positive side and a negative side. And so you have something that's actually neutral behaving like it's charged. You can also charge things actually by touching them. I did this in a number of ways in the demonstrations. I touched a rod to the pith balls. I touched a rod to the electroscope. And in all of those cases, we saw that it was charged. Keep in mind, though, when you charge a conductor, it's going to lose its charge more quickly than an insulator. And that's why the electroscope had the glass panes on it. So this keeps it from letting the charge go out to the air as readily as it would otherwise. So our little leaves were inside. You can charge things by taking advantage of this polarization. It's usually called charging by induction. So again, if I charge up this rod with a certain amount of charge and I bring it near two conductors that are touching, what's going to happen is that they're going to behave like they're one single conductor. And so what's going to happen is, as I bring it close, the negative is going to migrate from the one closest to the rod. So then if I separate them and then take the rod away, I now have one that's going to be positively charged, the one that was closest to it, which would be this one, and negatively charged the one away from it. Overall, we didn't gain any net charge, but each one of them would behave like they were charged. And this shows both polarization and charging by contact. So I have a glass rod that's charged up. Usually if it's a plastic rod, it's going to get a negative charge. If you have a glass rod and silk, you can get a positively charged glass rod because it'll lose electrons to the silk. So this is positively charged. If I bring it near this, which is one single conductor, even though it's made up of 3 separate parts or 4 separate parts, and you consider the leaves to be the individual things, since they're all metal and they're all touching, they behave as one. And so when I bring that close, it's going to cause the negative of our neutral to come up here. And so this is going to look like it's charged, because the electroscope, when the leaves are apart, that tells you that it has a charge. But it isn't really charged. If I touch this to here, what's going to happen is these three negatives are going to go up to here. And what happens is these three negatives each cancel out a positive, and I'm going to be left with two positives here, whereas I once had five positives, and I have three charges. And I had you guys draw this when we did predictions as far apart as possible, because they don't like each other. So they're going to get as far apart as possible. You did not gain any net charge. We started overall with 5 positive charges. Here we still have a net of 5 positive charges, because these 3 negatives would cancel out these 3 positives. And then over here, we still have 5, and we still have 5. All right, so our only equation in this section is going to be that Coulomb's law that I mentioned to you guys. So if you remember when we talked about Sir Isaac Newton, we talked about the attraction of any two masses in the universe. And when I first introduced this to you, I gave you a unique situation, a special situation, which is the main one we use in all cases, which was that weight is equal to mass times this acceleration due to gravity, which is also our gravitational field strength. Really, this equation is a special case of this one. Where G is a constant, which is 6.67 times 10 to the negative 11th meters squared over kilograms squared. M and M are masses in kilograms, and R is the distance between their center of masses. And that's in meters. So in this equation, the biggest role would be played by how far apart they are, because this gets squared. So if I double my mass, I'm going to double my force. If I make my radius half as much, my force goes up by a factor of 4. So this equation is going to look very similar. And it's called Coulomb's law, or the equation of electrostatic force. So it's electricity, it's static, because we're not talking about things moving. That makes it more complicated. So it is 1 over 4 pi epsilon 0 Q1 Q2 over R squared. We just rewrite this 1 over 4 pi epsilon 0 as a little k. And this k ends up being 9 times 10 to the 9th newtons meters squared over Coulomb squared. So we have a constant. We have two charges, Q1 and Q2, which are both going to be measured in C. And you can use lowercase q or uppercase q, just like we do with the mass, because very often one of the charges is much bigger than the other one. R is going to be the distance between the center of charges. Epsilon 0 is our vacuum permittivity constant, and that's the 8.85 times 10 to the negative 12. So if you take 1 divided by 4 divided by pi divided by 8.85 times 10 to the negative 12, you end up with this constant. We don't need to worry about this, but this accounts for how charge interacts with other charge in free space. And we have a permeability constant, which is mu naught, which, what was that? That attests to how magnets account for each other in free space. And it turns out that James Clerk Maxwell found that they're related to the speed of light. That the speed of light ends up being equal to 1 over the square root of the product of these two, which you guys don't need to worry about, but that's where the epsilon zero is. We're just going to use K. All right, so let's find the electrostatic force between two electrons. So we're going to look at what this force is. And I'm going to leave the sign out. So this is going to give me my force magnitude. The sign's going to give me the direction. And like MC Sketcat said, opposites attract. So we're going to say that if they're opposite charges, it's going to be a force of attraction. If they're the same charges, it's going to be a force of repulsion. I just heard a big boom, so I went and checked, and no one's here. I don't think anyone's on this entire floor right now, so kind of got me freaked out a little bit when I'm hearing booming. All right, so I'm going to put in 9 times 10 to the 9th newtons meters squared, coulomb squared. I'm going to put 1.6 times 10 to the negative 19th coulombs, and I'm going to do that twice. Leaving out the negative. So the electron charge magnitude is just 1.6 times 10 to the negative 19th without the negative. And then our distance is 1 times 10 to the negative 10th meters, and that's squared. So I have 2.3 times 10 to the negative 8 newtons. And it's good for you guys to practice actually putting this into your calculators, because that's where a lot of the errors make, because we're not used to using these huge exponents. I mean, you guys probably did it some in chemistry with Avogadro's number and moles and things, but the other thing that's tricky is it's hard for you to know what's a reasonable answer, because we don't really talk about, you know, this interaction of charge. And I would say that this is a repulsive force. It's a repulsive force. All right, what would be the weight associated with an electron on Earth? So this is going to be 9.11 times 10 to the negative 31st kilograms times 10. And again, there is a force of attraction between the mass of the two electrons as well. But I'm taking it with Earth, which is something that's hugely massive, right? 5.98 times 10 to the 24th kilograms. So how close are these two numbers? And I have 2.5 times 10 to the 21st. So we're saying that it is so that many zeros greater. So the electrostatic force in the grand scheme of things is much, much bigger than the force of attraction between masses. Now, keep in mind, masses all attract. There's no repulsion. Whereas charge, and there's equal amounts of positive and negative, the opposites attract and the likes repel. So it's not that gravity doesn't play a part in anything.